3.2% divided by 365 days will give us, let's see here, 0.008, and we'll round it to 4 decimal places. It's really important that you round out to at least capture a couple of the non-zero decimal places, because as you might guess, this is a really, really small percentage, and so we're really only getting about 0.0088% per day. Now, as a decimal, what does that come out to? Well, percent means over 100, so 0.0088 over 100 will give us 2 extra zeros if you take 0.0088 and divide by 100. So that means our growth factor will be 1.000088. That's the factor that we'll multiply by. So to get our future value, we would take our present value, multiply it by the daily rate, and, well, it depends how many days we're dealing with. So in this case, we're dealing with 3 years. So in the exponent, we would have 3 times 365. So I'm just going to go ahead and write that there, knowing that if you multiplied 3 times 365, that would give you the total number of days of this investment. We know we want to have 16,995 for the future value, so we need to figure out what the present value should be. Well, what I'm going to do is type in, I'm going to do this the roundabout way. I'm going to say 1 plus the second negative sign. That will take 1 plus my previous answer, which is simply 1.0088. Now I'm getting, oh, I'm sorry, I shouldn't do that. Excuse me. I am going to actually take that, divide that by 100 to get the decimal, which is it shows up here as kind of a funky notation. But if we take 1 plus that, that will give us our growth factor of 1.000088. And it gives us a few more decimal places. That's kind of nice. So we get that raised to the power of, and I need to put this in parentheses, 3 times 365, which gives me 1.100, and I'll take it about that many decimal places out. And I know that my future value will be my present value times this amount. So to figure out what this amount should be, I'm going to divide both sides. Now it looks complicated, right? Because all the way up until here you had exponents and all that jazz, but now all we have is multiplication. So we've reduced it down to a pretty simple problem, and we can take 16,995 and either divide it by second answer, or I'll just go ahead and use our rounded version of 1.008. That gives us the fact that P is about $15,438.77. So remember, when you solve for a present value, that's a dollar amount. So that means that, 3 years isn't a whole lot of time, but if we want to earn the amount needed for that car, we would have to put away this dollar amount today, which a lot of people would say, wow, that's a lot, and that's not something I can practically earn. That's probably true, and that's why a lot of times we use things like regular monthly deposits, which we won't consider here because it gets a lot more complicated, but that's kind of how we would go about things. Let's take a look at another variation of this problem. How many months would it take to earn enough for the car, $16,995, if you were only able to put away $3,000 today? Okay, well that only changes the problem in that our future value, our future value stays the same, but now our present value is fixed. So it's $3,000 times 1 point, and let's see how far we rounded, 0.00088. And in this case, we don't know how long, so I'm going to call this N for the number of years. I'm calling it capital N, or excuse me, the number of months. Because remember, this is our, I take that back, this is our daily growth rate, so that means this up here will be the number of days. And we need to figure out how many days it will take. So let's cross this out and say days to keep that simple. So how do we solve this? Well, algebraically, this problem gets a little more complex. But the way I always like to think about solving an equation is, what would I do if I had the number of days, if I knew the number of days? So for example, what if I had this? 3,000 times 1.00088, missing an extra zero there, and I took it to the 10th power. Well, step 1 would be to raise to the 10th power. The second step would be, well, once you had this taken care of, you would multiply by 3,000. Well, what would that give me? That would give me the future value, right? That would give me the value that I find on the left side of the equation. So what if I work backwards? In other words, I already know this, but I don't know this up here. Such as the case up here. Well, I would work backwards, right? Because if I know the number that I'm starting with to get the future value, then I work forwards. But if I know the end result and I want to know the beginning result, I'm going to work backwards. So instead of multiplying by 3,000, I would divide by 3,000. Okay, well that, in this case, would mean divide both sides by 3,000. So divide here and divide here. So that would cancel out, and then I would have whatever this is, 16,995 divided by 3,000 equals 1.000088 raised to the n power. So then, secondly, well, how do I handle this? What's the opposite of raising to the 10th power? In this case, sorry, the nth power. Well, that's an unknown, right? Because we don't even know what n is. So we're going to come back to this, but let's take a look at how we would do this graphically. So what I have graphed here is the function 3,000, my present value, times the growth factor raised to the number of days power. And then I have for my second equation the amount that I want to see when this horizontal line will intersect the graph of the growing present value here. My window I'm going to set from 0 days all the way up to, well, I've got to decide on the maximum number of days. So let's just say 20 years. So 20 years would be 20 times 365, because remember this is on a daily basis. And I'm only going to take my my dollar amount up to 20,000, because remember we're modeling amount owed as or amount payable as a function of the number of days. So if I graph this, well, there's my amount earned, there's the value that I want to achieve. I'm still way far out. That gap is still pretty big. So I'm going to set my days, I don't know, 7,300 days. So maybe I'll go up to 30,000 days just to see. And I graph this, and there it is. There's the intersection point. So at that point in time, my investment will be worth 16,995. Well, let's see what that is. We would go to second trace, calculate, the intersect, feature 5, and I would select the first curve, second curve, and go over and make my guess, which is about there. Hit enter. And this tells me that after 19,708 days, or 19,709 days, I would have 16,995. So 19,709 days, 19,709 days. Well, if we want to convert that to years, the years would equal 19,709 days divided by 365 days each year, which would tell me that 19,709 divided by 365 gives me, this is about 54 years. That's a long time. So this tells us that at a growth rate of 3.2%, in order to convert $3,000 into almost $17,000 at this small yearly rate, I would have to basically invest my money for almost the majority of my life to do that. So that's just kind of a cue as to, you know, the kinds of goals that we want to accomplish and what we have to do to accomplish them. Now, this does bring up some interesting points, which is how would we come up with this answer graphically if we had to or how would we come up with this answer if we weren't able to do it graphically? In other words, calculate this intersect feature. Our calculator obviously has to do some work to find that. So since this is algebra, we will discover how to do that in the next series. Let's turn our attention to a couple of questions here. So we notice that, first of all, our model, the one that we're using, assumes that interest is paid once every day or a week or a month or etc. What if growth occurs continuously? In other words, what if interest is paid all the time? More generally, not only interest, but what if anything grows continuously? Things like populations, which are not just changing once a year, but that are changing all the time. Bacteria are always growing. Radioactive elements are always decaying. Things like plutonium are always decaying whenever they're in inactive states. So, first of all, let's go back and address our compound formula. So, compound interest formula, if we define a few little pieces of information, the fact that we know that R is the interest rate, or what we are calling the APR, that's the annual rate, and N is the number of times interest is paid each year, and little t is the number of years that the money is in the account, well, then we know for compound interest that the future value of the investment is equal to the principal times 1 plus, so we're taking 100% and we're adding on, well, what do? We take the APR and we divide it by the number of times interest is paid each year. We raise it to the power of the number of months, days, etc. that we have. Well, N tells us how often it's computed each year. T tells us how many years it's for. So if it's if this is daily and this is the number of days, then multiplying it by the number of years will tell us the total number of days. As kind of what we did up here, really, if you think about it, we took 3 years, in this case this was our T, 365 times a year gave us our exponent of the total number of days. So this is the formula that we've really been using. Well, if you compound continuously, we often say compound continuously. This is if something grows, anything, not just interest, but if populations are growing continuously, our future amount is equal to our present amount times basically all of this thing here gets substituted with the following: e raised to the r. So this whole thing becomes e raised to the r times the number of years. This is all in the exponent here. Now, what is e? Well, e is a number just like pi. It's in finance equal to about 2.1728. So in your calculator, if you go to your home screen and you hit second and this button that says LN on it, you will get this guy that says E, or if you hit second and the division sign, you get the letter E, or the little lowercase letter. And if you hit enter, you get, suddenly this number pops up, 2.71828, which is the same thing you'd get if you typed in second LN and you put in a power of 1, 2.71828. So we won't really go on discussing where this thing originates from and how it comes about, but basically you'll notice that, for instance, if we would compound continuously at 3.2% APR for the starting value of $100 for 3 years, well, you might say, well, that $100 is going to grow into a very, very large amount. Well, if we took our formula, the future value is equal to 100 times this number e raised to the r times t. We call it the PERT formula sometimes. And the rate is 0.032 as a decimal. So 0.032 times 3 years, well, the way we do that is type in 100, second the ln, and in our power we put 0.032. We never use whole numbers in these formulas for percentages, times 3, and hit enter. You'd see that you'd have about $110.08. How does that compare to what we would have compounded daily. Well, based on our compound interest formula, 100 times our rate raised to the 3 times 365 gives us